A box of mass m equals 6 kilograms is pulled by a string along a rough horizontal surface, rough meaning friction. The tension of the string remains constant throughout the process and has a magnitude of T for tension. The string makes an angle of 28 degrees with the surface. The box is initially at rest. After, the box has moved a total of 2.3 meters. The work done by the work string, is 50 joules, and the work done by friction is 41 joules. Okay, what is the magnitude of the tension T? Okay, magnitude of tension T. Okay. So we're going to say here, so we know work. So work equals integral F dot dr. We know that the force is constant. So, well, first, this is a dot product. So that's going to be parallel with. You can think of dot product as cosine of theta, where theta is the angle between F and R. So this will be integral of, I'm going to say T for tension, cosine of theta dr. T is constant, cosine of theta is constant, so we're going to pull that out. So we have T cosine of theta integral dr. This is just the distance traveled. So this will be T cosine of theta times, and then I'm going to say delta r, where this will be r final minus r initial, which is just the distance traveled. So to solve this then, we're going to look for T, which will be T equals work done divided by cosine of theta, and I'm going to write delta r. So, boom, yep, looks good. So we know the work done is 50, work string. So this is the work done by the string by pulling. So we have 50 divided by cosine, nope, not quite, cosine of 28 degrees. And we're going to multiply that by 2.3, because that's the distance traveled. Yep, that seems reasonable. Let's get out a calculator. There we go. Clear. Go to mode. Make sure we're in degrees. Quit out of that. Do a 50 divided by quantity cosine of 28 times 2.3. 24.62. 24.62, and this will be newtons because it's a force which is measured in newtons. 24.62, bam. So it's going to be this one right here. That is the magnitude of the tension on the string. And one careful thing is you want to make sure that you're doing the total tension. You want to do the tension up at an angle, not just the tension that's being pulled. And we took that into account here by using the cosine of theta. Okay, what is the speed of the box after it has traveled 2.3 meters? Okay, so for this then, we're going to say, look at, we know how much work is done. So we know work string. So we look at this box here. So we have work string going this direction. And it is specifically this direction because work, as we said, is integral F dot dr. And this is going to give a scalar in the direction of dr. So this is the portion of F that's parallel to r. So tension X, which is force in this case, times dr. So it is going to be to the right. It's not going to be up. Work is going to be to the right. They're going to have, work friction going backwards, and they're going to oppose each other. So our total work, I'll write this as a delta W, will be work string minus work friction, which we have, there should be an R involved. There we go. 50 minus 41, which equals 9 joules. 9 joules of energy, Joules, as opposed to Jewels. So we have, this is going to be converted to kinetic energy, which is 1/2 mv squared Therefore, V squared equals 2 times, I'm going to call this energy kinetic, which we know is that number right there, divided by mass. Okay, so now I'll solve for velocity squared. 2 times 9 divided by, what's our mass? 6 divided by 6. Second answer, so we got square root of 3, which gives us 1.73. Implies V equals 1.73 meters per second. 1.73, got it right here. That's not too bad. Okay, what is the coefficient of friction between the box and the surface? Okay, so this one we got to be a little bit more careful. So, so we're still going to do the work equals integral F dot dr. So a lot of times you might see work equals force times distance. This is when force and distance are in the same direction. So all I'm really doing here, so there are two assumptions when you write this. One assumption is that this is constant, which it almost always will be in physics 1. And you're assuming that force is parallel to the distance traveled, which it sometimes often is. We made it parallel up here by using the cosine of theta. So if you're wondering why I write down integral F dot dr, you might not have had calculus 2 yet, so you don't quite understand what's going on. That's basically what I'm doing here. So as long as it's constant, force is constant, and it's parallel, then this work equals force times distance is true. Okay. So now I'm gonna do a little sidebar over here. Like it's under bar since it's below. So for friction, force friction equals normal force times coefficient of friction. And since it's moving, it's going to be the kinetic coefficient of friction. So this will be basically mass times gravity times coefficient of friction. But we also are being pulled up by the string. So drawing a picture, we have tension going this way. So we have a tension X. We also have a tension Y. And so we have a tension Y, kind of like this, pulling up, but we have a force gravity pulling down. So this mass gravity is going to be counteracted by force friction pulling up. So this really, force normal means the force that the ground is going to be pushing up. I guess it could be any surface pushing against an object to keep it from moving. So this block is being pulled down. If there wasn't a normal force pushing it up, then it would just fall through the world and I guess move towards the center of the earth. It's that normal force that keeps it solid. So it pushes on the ground pushes back. And so this normal force here is going to be less because the string is pulling it up through tension. So I'm going to look at it this way, over here. Force friction equals, I'm going to say, normal force times coefficient of friction, where normal force will equal mass times gravity minus tension in the y direction. Now tension in the y direction is going to be the main tension times sine of theta, because that way, if we look at our triangle up here, this side right there, cosine, that one right there, sine. So if you're familiar with SOHCAHTOA, you would then use sine equals opposite over hypotenuse, and we're solving for the opposite. That gives us t sine theta, assuming that t is this hypotenuse there. Okay, so that's how we get this mg minus t sine theta. So I think we can just solve that out. Maybe. So work friction is going to be in the same direction as motion. Not really. It's going to be the opposite direction. So there'll be a negative involved, but I'm not going to focus too much on that. So you could actually say up here that the work done by friction is not 41 joules. It's actually negative 41 joules. But that's okay. I was kind of worried about the signs at the end. So we have our normal force, we have our force here, and we have our work here, which we know is this. Force is going to be constant, and it's going to be in the same direction, so we call F dot D. I do it dot D over here. So this is work. So messy. So messy. So rallying the troops, we have work equals force times distance, because constant and parallel. And we have normal times mu k, which is coefficient of friction, times distance, which in this case is going to be mg minus t sine of theta times mu k times distance. And we know everything here except our coefficient of friction. Solving for this, now already done green. Already done green. Light blue. Okay. So coefficient of friction kinetic equals work due to friction over distance times mass times gravity minus t sine of theta. So I'm going to do this probably in parts. So let's see here. Hup. Zoom out a little bit so I can get a good scope of life. So we know what tension is. So we have on clear mass, which is 6 times gravity, which I'm going to say is 9.81. 9.8 is sufficient though. Minus 24.6 times, should check to make sure we're still in degrees. So this is the bottom portion, 6 times 9.81 minus 20. Hopefully this will give us a positive number. It does, times distance, which is 2.3. And then we have the work, which is 41 divided by second answer. It gives us 0.377, 0.377 equals 0.377, which usually coefficient of friction is usually about 0.377 or so, or about 0.3. Up, 0.377, 0.377. I'm good with that. Okay. So that's how you find the coefficient of friction. The key there is not only is the block being pulled down by gravity, but you're actually pulling the block up a little bit because of the tension of the string. Okay. So let's say the experiment is repeated, but this time pulling on the string with twice the force. The kinetic energy of the box after being pulled for 2.3 meters would be, okay, so now we have our box, we're pulling twice the force, 2 tension. After 2.3, what would be box now? Okay. So we don't really have enough data for this, because do we assume that, so we're pulling twice as hard, does that mean that we are, so I have 2 tension here, so I have 2 times tension y there, 2 times tension x here. Well, this 2 times tension y is going to pull up more, but part of our initial statement was we had 41 joules of friction pulling us backwards. So if we're pulling twice as hard on the leash or rope or string, we would pull the box up a little bit more, which would reduce the friction, which would actually mean we would have less than 41 joules of friction, because there would be less of a normal force on the ground. Or is it assuming that we're pulling twice as more, but something adjusts so that we still have this 41 joules? I'm going to go with the assumption, because it's the most restrictive, it's a lower value, that we still have this 41 joules of friction. So work equals F dot dr. So we have parallel and constant. So this is going to be, so if we double the force, we'll have 2 F times d, which will be twice the work. So we'd have twice the work. If we double the tension of the string, we will double the work that's done to move the box. So we would have 100 joules. And this is string, which would be 100 joules. Then when we subtract off the friction, we would have, so delta work would be work string minus work friction, which would be 100 minus 41, which would be 59 joules. So originally, we had 9 joules because we had 50 minus 41, which was 9. Now this time, we have 100 minus 41, which gives us 59. So, string is repeated, but this time pulling the string with twice the force, kinetic energy of the box that we pulled for 2.3 meters, which was our normal amount, would be more than twice the kinetic energy of the original case. And the reason we'd be putting in twice as much energy into it, because we doubled the force in this case would be double the work, but we're assuming a constant friction reducing the work, the constant work of friction opposing us. So the friction doesn't grow with us pulling the string twice as hard. So in the end, we'd be left with more than twice the kinetic energy of the original case. And even if we assume we ended up lifting the box, all that would do would reduce the work of friction opposing us, which would actually mean that the value of 59 would be closer to 100 joules than it currently is. So either way, we're going to have more kinetic energy, more than twice the kinetic energy of the original case. Hope that helped. I will see you on the next problem.